The last 4+2 addition we're going to see is ozonolysis. And ozonolysis is useful in synthesis. It's a good way of taking a double bond and making a carbonyl out of it. And so in this case, and in all the cases with ozonolysis, what we can do to figure out what the structures are going to look like for the products is we can take the double bond and basically cut it like we're cutting with scissors and adding an oxygen to each side. And so that's going to be effectively what we're doing in the reaction. The mechanism is going to be that 4+2 cycle addition that we've been seeing. And so when we're talking about what's the 2 pi electron component, what's the 4 pi electron component, 2 pi electron component is going to be the one on the right, because there is only 2 pi electrons in that molecule. The one on the left, we can clearly see 2 pi electrons at the top. The other 2 pi electrons are going to be the lone pair, because we saw that lone pairs, when they're in resonance, so we could push these down, push these up onto the oxygen. When lone pairs are in resonance like that, we count them as pi electrons. If they were in an aromatic system, for example, we count them as pi electrons. And so, and that's because they're in a p orbital. So we do also have one of the lone pairs counting as pi electrons, and then the other pi electrons are coming from between the two oxygens. So that's our 4 pi electron system. And again, those lone pairs are counting for 2 of those pi electrons. So how does this mechanism go? So we're going to start at the 4 pi electron species like we normally do. We're going to this time just start at the lone pairs themselves instead of at the actual pi bond. We're going to attack the 2 pi electron species. The electrons are going to go out through the pi bond and go back to attack the 4 pi electron species. And then that last bond is going to break to put what in this case is going to be lone pairs on that purple oxygen. And so what we're going to be left with, that oxygen at the top, then we're going to have our purple oxygen and our blue oxygen atom all connected with single bonds. Now our new pi bonds, or sorry, our new sigma bonds are going to be formed to the carbons that were in the double bond. And so we're going to have a species that looks like that. That's going to get rid of the charges on ozone. We can draw the lone pairs in, and so that 4 pi electron species is the actual ozone itself. So that's that structure for O3. So it is important to know that structure so we can draw this mechanism. And then we get to this intermediate. This intermediate is not very stable. We do have 3 heteroatoms connected to one another with single bonds, typically not a very stable arrangement. And so what's going to happen is it's going to start to break apart. So that first step that we drew, that breaks the pi bond. So now the pi bond's not there. This next step is going to break the sigma bond. And so what's going to happen, we're going to push those electrons from the blue oxygen's lone pair is going to come down. We're going to break that sigma bond, and we're going to have that sigma bond go into making a double bond to the oxygen at the top. And then that oxygen releases the purple oxygen. So now we're going to have 2 fragments again that are on their own. We're going to have the one at the top with the oxygen. It's 2 lone pairs, and it's CH3 that's still attached. So if we want to number the carbons 1, 2, 3, and 4, this would be carbon 4 at the end and 3 that's doubly bound now to the oxygen. Then our other fragment is going to have the purple oxygen, the blue oxygen, and that blue oxygen is going to be doubly bound to carbon 2, and that's going to be our carbon 2 and 1. This blue oxygen, because it's going to have 3 bonds and a lone pair left, that's going to be positive. The purple one is going to have 3 lone pairs. Total is going to be negative. And so this is very unstable as well. And so this basically recombines. And if we're thinking about how it's going to recombine, we have this negatively charged oxygen. This negatively charged oxygen is going to go after the delta plus on the other fragment. And so this fragment here, the most electron poor area is carbon 3 because we do have that resonance up onto the oxygen. We have a delta plus at carbon 3. Let's go ahead and show that in. So we have a delta plus at carbon 3. The oxygen itself is delta minus. So when the purple oxygen goes to attack carbon 3, the electrons are going to go up onto that black oxygen at the top. And then that oxygen is actually, because it'll be negative momentarily, it can go and attack the delta plus on the other molecule. The delta plus on the other molecule is at carbon 2. And that's existing because we also have that resonance where we could bring those onto the oxygen, make the oxygen nice and neutral. And so carbon 2 has a pretty large delta plus on it as well. So when we're drawing our mechanism arrows, we're going to start from purple oxygen, those lone pairs. We're going to attack carbon 3. Then we're going to break the pi bond up and we're going to go through that oxygen all the way to carbon 2. So that black oxygen is going to be connected to carbon 2, and then we're going to dump those electrons from between carbon 2 and the blue oxygen completely onto the blue oxygen. And so that's our recombination step. And what we're going to have, we're going to draw in that black oxygen at the top. It's carbon 3 and 4 there. That oxygen, if we're kind of thinking about what else is attached to carbon 3, well, we see that this purple oxygen has attached to carbon 3, and so we're going to have that purple oxygen attached to carbon 3. So that's going to be our purple oxygen. Purple oxygen is still bound to blue oxygen. And blue oxygen is still bound by one bond to carbon 2. So let's go ahead and draw that bond to carbon 2. Carbon 2 is still bound to carbon 1. So this is carbon 2, carbon 1. And then that black oxygen went to attack carbon 2. And so this oxygen at the top is also connected to carbon 2. So let's go ahead and draw on that bond as well. So that's going to be our molecule after the recombination. And we were really tracing what was bound to what. We were numbering our carbons, trying to figure out how everything was going to be connected. This is relatively stable, and it's going to stay like this until step 2. And in this step, we're going to have that DMS, which is dimethyl sulfide. So that's this compound here. This is going to come and break up that 3-membered, or that 3 oxygen members in that 5-membered ring. And so what's going to happen, we're going to attack, let's just say we attack the purple oxygen. That's going to end up breaking the bond between purple oxygen and carbon 3. That's going to go right into making a double bond to the black oxygen at the top, which is going to cause the bond on the other side to break and go towards the blue oxygen. And then eventually that's going to cause the bond in the ring to break as well. And so what we're going to be left with total, we're going to have our double bond to our blue oxygen over here with our carbons 2 and 1. And we're going to have our black oxygen doubly bound to carbons 3 and 4. That fragment, and then our last fragment is going to be the one with the sulfur and the 2 CH3s. And then that's going to be bound to the purple oxygen because we showed it attacking the purple oxygen. So we see that those two carbon fragments that we get out of it, these are these two over here. Let's take a look at some more examples. So in this one, we have basically we're just asked to give the product. So what we're going to do is we're going to cut the bond and we're going to add oxygens to each side when we have this ozonolysis. So we're going to have our two products look like this. So we have our carbons 1, 2, 3, 4, and 5. Doesn't matter how you number them for this. 1, 2, and 3 are going to be in one molecule, and then 4 and 5 with the other. Carbons 3 and 4 are doubly bound to each other. They're each going to be doubly bound to an oxygen in the products. Same thing we can do for the second one. We're going to cut that bond, but since everything is connected to one another, we're actually just going to have one big molecule, and we're going to have at the end, we're going to have like carbon 1 with its double bond to the oxygen, then 2, 3, 4, and then 5 with its double bond to the oxygen. So this is 1 still bound to 5, 4, 3, and then carbon 2 is going to be on the other end of the molecule because of how we numbered it, and that's going to have its double bond to the oxygen. So we still took that double bond, we cut it, and we added an oxygen to each side, and that's going to be our product there. So when we're trying to figure out those products, that's what we're doing. The mechanism, we're going to have to be a little bit more careful with what exactly we're drawing for our arrow pushing, but this is how we're going to do just for the products and how to figure out the products. We're going to just chop that double bond, add the oxygens to each side.